Hello, everyone, and welcome to our third Inspiration Exchange session. My name is Nick Maxfield. I'll be moderating today's session, and I handle communications for the Schaar Lab. We'll also have presentations and Q&A from some of our lab's members, Ahmed Alaa, Dan Jarrett, Ioana Bica, and Zhaozhi Qian, and we'll be joined by Mihaela van der Schaar, who will be supporting the session and handling a general Q&A at the end if we have time. So to give you an idea of what to expect from today's session, firstly, our purpose for the session is a kind of continuation of the mini theme we've been running on AutoML methods and technologies. This is something that we started with our first two sessions, and as time has gone on, we've kind of gone from the conceptual and high-level aspects of AutoML to the more detailed and granular aspects of AutoML, which is why this time our focus is going to be on software packages. And if you want to know more about these, please visit the URL on this slide here. And our real hope from these as well is that you'll actually try out and experiment with and give feedback on our software packages, and that we can kind of build a bit of a community around these. So to walk you through the format or agenda for today's session, after my intro right now, we'll have a couple presentations. The first one will be on AutoPrognosis software, and that'll be given by Ahmed Alaa. And the second sort of section will be on Clairvoyance software. And we'll actually have two videos on this, one given jointly by Ioana Bica and Dan Jarrett, and one by Zhaozhi Qian. And after this, we'll have a Q&A and discussion on AutoPrognosis and Clairvoyance software. And time permitting, we'll have a short general Q&A on ML for healthcare with Mihaela. A couple of notes on the Q&A session. Firstly, we'd like to ask you to keep your questions to 1 minute per question, if at all possible, so that we can allow 2 minutes for each question and answer in order to get through as many of these as we can. And secondly, if you have any questions, please do post them into the Slack workspace in the Inspiration Exchange AutoML channel. The earlier you post them, the higher the likelihood that we'll actually be able to get around to them. So please do post your questions early. And then we're done with the Q&A session. It'll just be a few kind of closing words from me, and I'll introduce what you can expect from our next Inspiration Exchange session, and then we'll wrap up. Hopefully, we'll finish within just about 1 hour. So without further ado, the next part of our session is Ahmed's presentation on AutoPrognosis. Again, if you have any questions on this that you can think of during the presentation, please do post them into our Slack chat. Thank you very much.
So hi, I'm Ahmed. I'm a postdoc at the Schaar Lab. And today I'll be talking about the AutoPrognosis software, giving you a brief overview on the software and how to use it. And the software is available through this GitHub link. So as we discussed last time, AutoPrognosis is an automated machine learning algorithm that designs machine learning pipelines tailored to the data set at hand. And it does so by selecting among a pool of different imputation, feature processing, classification, and calibration algorithms. And it does so using a Bayesian optimization algorithms that navigates this huge design space to select the best model that fits the data set at hand. So the total design space of AutoPrognosis is more than 5,000 possible machine learning pipelines, which is comprised of combinations of 7 imputation algorithms, 13 feature processing algorithms, and 20 classification algorithms. A brief overview over Bayesian optimization. Bayesian optimization is a technique used to optimize black box functions using sequential exploration of function values. In this algorithm, in AutoPrognosis, we use a Gaussian process prior for the Bayesian optimization algorithm. And our black box function is a function that maps pipeline selections to performance metrics. The performance metrics can be chosen by the user. So it can be, for instance, the area under receiver operating characteristic curve, or the accuracy, or the mean square error. We discussed last time in detail the technical details of Bayesian optimization. But the library that we use to implement Bayesian optimization in AutoPrognosis is called GPyOpt. So you can design your own variant of Bayesian optimization using this library. The specific approach to Bayesian optimization that we use in our model is called Bayesian optimization with structured kernels. So because our design space is so big, we have a very high dimensional problem. So the number of explorations that we need to implement with Bayesian optimization to reach the best pipeline grows exponentially with the number of dimensions. So as we discussed last time, the way we increase the efficiency of Bayesian optimization is through the structured kernel approach, where we cluster different algorithms into separate kernels, where the performances of these algorithms are correlated, whereas the performances of algorithms in different clusters are not correlated. So we can, in parallel, explore different groups of algorithms and ignore their correlation with other algorithms. So this is a flow chart for how the AutoPrognosis algorithm proceeds. So we start by clustering the different dimensions of the optimization problem. This means that we group together the different algorithms and hyperparameters into different distinct kernels of the Gaussian process prior. And then we iteratively explore the different pipelines within each kernel. And then once we collect information on the performance of different pipelines belonging to the different kernels, we update the kernel. So maybe we start by clustering neural networks together with XGBoost and maybe random forest with logistic regression. But after exploring the performances of these different algorithms, we actually discover that the kernel needs to be changed, and maybe we need to pair neural networks with logistic regression and XGBoost with random forest. So here we are doing this clustering in an automated way, and we are learning it as we explore the different pipelines through Bayesian optimization. And then we have different functions, one called merge domains, one called kernel decomposition, one called split domains. These are the functions that map the indices of the different hyperparameters and algorithm selections in the Bayesian optimization problems to the new kernel assignment after we learn the kernel after a certain number of iterations. So the AutoPrognosis algorithm uses an sklearn style API. So there is a fit method, a predict method that's used to train the model and make predictions with the model, just in the same way you would do with an sklearn machine learning model. When you're instantiating an AutoPrognosis model, we select different parameters. These include the metric to optimize. Here, the default selection is AUC. The number of folds of cross-validation included in evaluating every selection of a pipeline. The number of iterations of Bayesian optimization. The number of Bayesian optimization iterations after which we update the kernel. Whether we construct an ensemble of methods or just select the best pipeline. The ensemble size if you are selecting an ensemble. And then we also use Gibbs sampling to learn these kernels. The number of iterations of the Gibbs sampling procedure is also selected. The default is 100 iterations. The burn-in samples of the Gibbs iterations, these are the initial samples that are thrown away when computing the final posterior probability of kernel assignments. And the number of components is the number of kernels. The model is GP. You can change this to another prior, maybe random forest or something else. The type of kernel, so this is a Mattern 5/2 kernel, but there are other kernels like squared exponential kernel and other selections. You can even select a neural network as the kernel for the Gaussian process. The acquisition function is the function that is used to explore pipelines over time through the Bayesian optimization. LCB is the default selection. It refers to lower confidence bound. So this is a notebook that we have on our GitHub repository. It contains an example of how to use AutoPrognosis. So we apply this to a breast cancer data set. And as you can see, the algorithm outputs the pipelines that it explores every iteration. So Miss Forest imputation algorithm with gradient boosting is the first thing it explored. And then it explored median imputation with multinomial naive bias, and so on. And every iteration, it will output the current best pipeline and the value of the Bayesian optimization objective, so the performance of the best pipeline that has been explored so far. And after you train the model, you can use the predicts function to make the prediction on the testing data, and then you can use the standard sklearn metrics library to compute, to evaluate your performance. So you can check out this link. It contains an example of how to use AutoPrognosis on breast cancer data. And if you face any difficulties using the model, you can post an issue in our GitHub repository. Thank you for listening.
Okay, so our next section is on our Clairvoyance software. We have two presentations within this. One is given jointly by Ioana Bica and Dan Jarrett. It's kind of an introduction or explainer or tutorial on the software. And the other is by Zhaozhi Qian, and it's basically about how to add your own algorithms within the Clairvoyance framework. Again, if you have any questions, please do post them into the Slack chat as soon as you can so that we can get round to selecting them.
Hello, my name is Ioana Bica, and together with Dan Jarrett, we'll introduce Clairvoyance, a pipeline toolkit for medical time series. We'll give you a brief overview of Clairvoyance, and then we'll walk you through tutorials for how to use Clairvoyance for prediction and treatment effect estimation. So the Clairvoyance software package has been developed with the patient journey through the healthcare system in mind, where we want to know what patient outcomes are most likely, which treatments best improve outcomes, and when taking additional clinical measurements is the most effective. So by using static data such as age and gender and temporal data such as vital sign, lab tests, and treatments, Clairvoyance provides corresponding modeling pathways for personalized prediction of outcomes, personalized estimation of treatment effects, and personalized monitoring, all integrated with a unified software toolkit. Here we present an overview of the pipeline from Clairvoyance, which consists of all of the essential steps in handling time series data in order to build machine learning models for prediction, treatment effect estimation, and active sensing. These essential steps are integrated within a pipeline consisting of pre-processing, imputation, uncertainty estimation, calibration, and interpretation. So Clairvoyance is a software toolkit that enables workflow development within a single unified interface that is similar to sklearn. Moreover, the different components in the Clairvoyance pipeline are modular and have structures that can be composed together to facilitate rapid experimentation and deployment of machine learning methods for medical time series data. So the Clairvoyance package is publicly available online and contains tutorials for each of the integrated pathways for personalized prediction, personalized estimation of treatment effects, and personalized monitoring. We'll walk you through tutorials for personalized prediction and personalized estimation of treatment effects.
Okay, so here's a quick introduction to using the Clairvoyance API to do time series prediction. Just to be clear what we mean by time series prediction, the inputs here are static features of the patient, such as demographic information, pre-existing conditions, and other admission time features, as well as temporal features, such as vital signs and lab tests monitored over time. And the outputs are either one-shot predictions, here on the left, such as a predicting patient mortality at the end of a hospital stay, or online, also known as rolling window predictions, such as predicting the need for mechanical ventilation, for example, 24 hours ahead from any given time point. So just to give a high-level overview of what the API tries to accomplish, here's a schema of the entire workflow from start to finish. On the top left, we start with our input data in standard EAV format, so entity attribute value format. Then we're going to load and pre-process the data, define the prediction problem, impute missing measurements, do any feature selection if needed, and train the main prediction model. And afterwards, we can also estimate and visualize some uncertainties or measures of importance of different features with respect to the outcome of interest. Okay. So importing and loading, that's just some boilerplate. Here's an example in step 2 here, where we're first defining the pre-processing steps we want to do, and then using the pipeline composer object to execute these steps. And here in the problem definition, we're defining an online prediction problem where the outcome of interest is the need for mechanical ventilation with a window of size 4 steps. Then we're going to impute the missing values in the data. And since we have both static and temporal features, we want to select an imputation model for both types of data. And pretty much the same interface when it comes to the feature selection set. To keep this short, we're not going to walk through every step of the workflow. The tutorial is, the detailed tutorial is online. But at this point, it's important to note what the design pattern is. Most component modules are designed around the familiar fit transform, fit predict paradigm, and using the pipeline composer object. So modeling the whole workflow is very much based around a single chain of API calls as much as possible. But just to show what the training and prediction step looks like, here we see that the function calls are not unlike what you'd expect from a standard package like sklearn. So this way, if you want to integrate a more sophisticated prediction method into the pipeline, or if you've embedded a really cool imputation method, for instance, these can all be integrated using a simple wrapper function.
I will now briefly show a tutorial on how to use Clairvoyance for estimating treatment effects over time. So given static and temporal data, Clairvoyance can be used to estimate the effect of a single treatment or a sequence of treatments on the patient outcome. So for instance, using the static data such as age, gender, and demographic information, temporal data such as vital signs and lab tests, and treatments administered over time such as antibiotics, we can estimate whether the patient will need the ventilator under different possible treatment plans for antibiotics. And then these counterfactual trajectories can be used to decide which treatment plan will give the best patient outcome. This figure represents a summary for the Clairvoyance pipeline for treatment effect estimation, and I will go through the main steps in here. So the observational data set can be loaded by specifying the path for the static features and for the time series features. To be able to reliably estimate treatment effects over time, for the selected data, users should check the necessary assumptions for performing causal inference using the data, namely overlap and non-hidden confounders. Overlap means that each time step, each patient has a non-zero probability of being assigned each treatment option, while non-hidden confounders involves considering all of the variables that are affecting the treatment assignment and the patient outcome each time step. And if these assumptions do not hold in the observational data, the users will obtain biased estimates of the treatment effects. As a next step, we do data pre-processing by one-hot encoding features and normalizing values. The third step involves defining the causal inference problem that we are trying to solve by specifying which columns in the data are the treatments, which ones are the patient outcomes, namely the label, and whether we have a classification or regression problem, namely whether the patient outcome is a categorical or real value. So the current implementation of Clairvoyance considers binary treatments that are assigned to the patient each time step and consists of methods that can estimate the effects of this time-varying treatment on the patient outcome. And this step was going to define the maximum sequence length and also the prediction window, which determines the difference between consecutive time steps. Steps 4 and 5 involve doing imputation and feature selection of the data by specifying which algorithm to use for imputation and feature selection out of the ones implemented in Clairvoyance. For imputation, there are different sets of algorithms implemented for the static setting and for the temporal setting, and similarly for feature selection. However, for performing causal inference, if feature selection is used, one needs to ensure that the remaining features still satisfy the required identifiability assumptions, namely overlap and non-hidden confounders. We then define the treatment effect model to fit on the training data. So among the methods implemented in Clairvoyance are the counterfactual recurrent network and recurrent marginal structural networks, which can be used as the treatment effect models. We can specify here the hyperparameters to use for the different components of the models. and then we can train them on the observational data. Since these models are capable of estimating counterfactual outcomes for a sequence of treatments in the future, we will also need to set a projection horizon for them. Finally, we can assess the trained model on the factual predictions by using a range of evaluation metrics, but most importantly, we can also use the model to make counterfactual predictions. In particular, we can specify different treatment plans in the treatment options variable here, and then use the treatment effect model to estimate the patient outcomes under these different treatment plans. The predicted counterfactual trajectories, as seen here, can be used to decide the best treatment plan and thus provide clinical decision support. Now, the problem of causal inference in the temporal setting has been a lot less studied compared to the causal inference in the static setting, and therefore there are many possible research directions for improving the treatment effects pipeline in clairvoyance. These include developing better model selection methods to be able to determine which method for estimating individualized treatment effects works best, because having a good model selection method is an important first step for building AutoML methods for treatment effect estimation. And other directions for future research are also building methods that can provide uncertainty estimates for the potential outcomes, as well as methods for determining feature importance for the counterfactual outcome. Thank you for listening to our presentation.
Okay, and our final presentation is from Zhaozhi Qian, and it's about basically adding your own algorithms to the Clairvoyance software framework. Again, if you do want your questions to be answered, please do post them into the Slack chat. We have a couple already, which is great, but the earlier the better.
Hello, everyone. Now I'm going to show you how easy it is to add new algorithms in the Clairvoyance framework. The Clairvoyance API follows the standard fit-predict paradigm widely used in machine learning software. Its implementation is modular and extendable, such that developers and researchers can easily add new algorithms in the framework and experiment with it. I'm going to give an illustrative example to add gradient boosting algorithm from scikit-learn in the Clairvoyance prediction pipeline. To begin with, we first declare a gradient boosting class, which inherits two base classes, the base estimator and the predictor mixin. Those two base classes are needed for all the prediction algorithms in Clairvoyance because they implement low-level helper functions. The class initialization is very standard. After we call the init method of the base class, we proceed to record all the user-provided arguments, including task definition, hyperparameters, and other configuration. The real implementation begins with the fit and the predict method. Note that since we are using the gradient boosting algorithm implemented in scikit-learn, and scikit-learn already implements the fit and predict method for all its algorithms, essentially what we need to do is to create a wrapper around the scikit-learn fit predict method so that it can interact with the rest of the Clairvoyance. To do so, we start with pre-processing the Clairvoyance temporal dataset into NumPy arrays. This can be done by using the helper functions inherited from the base class, and it only takes a few function calls. Next, depending on whether the task is a classification task or regression task, we instantiate the corresponding scikit-learn predictor. Finally, we just need to call the fit method defined in scikit-learn. The same rationale holds for the predict method as well, where again, we start by pre-process the dataset into NumPy arrays and call the predict method on it. To handle model persistence and loading, we we need to define safe and load model, safe model and load model methods. Again, this is straightforward because we can use the Pico module in Python. Last but not least, we also need to define a static method for the hyperparameter space. The hyperparameter space definition, you need to specify the name of the hyperparameter, whether the hyperparameter is discrete or continuous, and the valid domain of the hyperparameter. After the hyperparameter space is defined, the Clairvoyance automated machine learning framework can automatically find the hyperparameter within this space and optimize it. Essentially, that's all we need to do to add a new estimator in the Clairvoyance framework. As we can see, the procedure is very straightforward, and it does not only hold for the holds for algorithms in scikit-learn, but also any algorithm that implements the fit and predict methods. So if you have a new algorithm, you can immediately bring it in. You can bring it in the Clairvoyance and immediately leverage the power of automated machine learning. Moreover, the other components of Clairvoyance, for example, the active sensing components and treatment effects components, are also implemented in modular and extendable way, so that you can also add new algorithms in those components as well. That's all the presentation. Thank you.
Okay, so now it's time for our Q&A session, and thankfully we have a few excellent questions already lined up in our Slack channel. I did get a message from someone asking how to access the Slack channel. Please just have a look for one of the URLs in the emails I've sent about this session. It's right in there. So just to explain how this Q&A session is going to work. When we call on you to ask a question, I'm going to basically allow you to unmute yourself, and please then do unmute yourself and try and specify which software package you want to ask about. I would like to remind people to try and keep each question, if possible, to 1 minute so that we can have 2 minutes in total for each question and answer. I believe we already have a question lined up from Evgeny. So Evgeny, if you wouldn't mind unmuting yourself.
Hi, Nick. Yes, so my question is, I think, applicable to both software packages, both AutoPrognosis and Clairvoyance. So how easy would it be to use these with some kind of more different data sources rather than just something simple and tabular, let's say imaging data or even sort of video data or genomics data or anything like that? Is that easy to kind of build something on top of these to be able to handle this type of data?
Yes. So I think the only thing extra that you need to do to incorporate this type of data into any of our models is just the basic data formatting. So if you put any of these data in the form of a feature vector, then all of these methods can work. In the case of AutoPrognosis specifically, the first module has to do with feature processing. So when we deal with this kind of very high dimensional multimodal data, the role of feature processing will become very prominent, because then you need to do feature compression, feature selection, when you deal with like very high dimensional genetic data or image data. So yeah, all of these methods are perfectly suited to handle multimodal data and probably any kind of data that you can put in the form of a feature vector.
Thank you.
Okay, so if we're happy with that, then I believe we have a question lined up from Prerna. If you wouldn't mind unmuting yourself and asking ahead, and I think this is for Ahmed as well.
Yeah, thanks, Nick. And thanks for the great presentations by all three researchers. My question was about AutoPrognosis in particular. I was curious whether it would be possible to integrate time to event data or survival data like as a potential like target to optimize for these models, like seeing as like it's an endpoint which is used by a lot of clinicians in their day-to-day operations, and also is more richer than like just binary like event data. Like, is it possible to integrate this in AutoPrognosis, or do you see value if it's not like in like adding this as a potential addition to the software?
Yeah. So thanks, Berna. That's an excellent question. So of course, actually, most of the data sets that we deal with in the clinical world are survival data. So there is a naive way to just use AutoPrognosis as is to handle survival models by just changing the selection objective to something like the concordance index or C index, assess model performance, and just replace the binary classification models with survival models. But turns out that this problem is actually more complicated than the binary classification problem, because survival models predict multiple time horizons. So it's hard to, if you don't have a specific time horizon of interest, you have multi-dimensional outputs. So you need to make model selections that are different at each prediction horizon. So we already have addressed this problem through another paper, and we developed a model called survival quills. And I'm posting now the paper related to this model in the chat box, where it uses something very similar to the AutoPrognosis Bayesian optimization routine to automatically select different survival models at different prediction horizons to form a non-parametric survival curves by combining many different survival models with weights that change for each prediction horizon. So you can take a look at this paper and send us feedback through email if you like.
Yeah, thanks so much for sharing that. Definitely take a deeper look. Thank you.
Great. Okay, so before I go to our next question, which is also, I believe, about AutoPrognosis, I'd like to especially call for any questions people might have about Clairvoyance software as well, since we haven't had any on that topic just yet. So yeah, please just stick those in the chat and we'll pick them up as soon as possible. Our next question is again on AutoPrognosis, and it is from Yushu, if you wouldn't mind unmuting yourself.
Yeah, thank you. And I have a question about the AutoPrognosis. I think it clusters similar algorithms into several subspaces and learn these subspaces. So how do AutoPrognosis choose the number of the kernel automatically? And does the number of the kernels remain the same in each the iteration? Thank you.
Yeah, thank you, Yushu. That's also an excellent question. So the AutoPrognosis model is a hierarchical Bayesian model. So we have a prior over which models belong to which subspaces. And then we have a prior over the performance of each model. Right now, we just fix the number of subspaces ahead of time because we know that we have like 15 classification models. So we roughly need like 3 to 5 subspaces, and you can set this in the flexibly in the algorithm. But a very interesting extension to this, as we get more and more models, we may need more subspaces. Yeah. So we can create a third layer in the hierarchy of the Bayesian model, where we have a prior over the number of subspaces itself, and then a prior over the belongingness of each model into each subspace, and then a prior over model performance. And this prior over the number of subspaces can be through a Dirichlet distribution or something that models discrete distributions. And then regarding your next question, whether this number would be fixed at each iteration, by modeling it this way, you would actually have a soft posterior over the number of clusters. So this would be updated every iteration. So you have a like a posterior distribution over the number of clusters at each iteration, and this would change over time as you discover the extent to which algorithms are different or similar.
Okay, thank you. Thank you for your answer.
Okay, so someone was very obliging and did give us a question on clairvoyance. Thank you very much for that. And that is D1, if you wouldn't mind unmuting yourself and go ahead.
Hi, thank you for the talk. I think my question is that when dealing with time series data, the visualization of the interpretation of the learned features of the model, or how the model predicts, it's very interesting and also very clinically relevant. So my question would be, what are the options from Clairvoyance that we can do such visualization of the learning?
Yeah, so just by way of preface, there are in the literature lots of different ways you can define interpretability, explainability, or what domain experts can understand. So far, what we've implemented or are very soon going to implement is a more narrow version based on feature importance. So in the time series setting, that would be the importance of different features over time. So a different importance for each time step, as well as possibly different importances based on the individual patient. So different things might matter differently depending on who we're talking about and their history. But that is definitely a very important research question. There are so many different ways you could say how to make something understandable. And that's what we all should be working on.
Yeah, thanks.
Okay, I think we have another question just in as well. Let me find it. Okay, yeah, so it's on Clairvoyance and it is from Jim. Sorry, Jim, can you go ahead?
Yes, thank you very much. So for Clairvoyance, as you're doing time series analysis, I saw the graph where there is a prediction at a certain point. And I was wondering, can you play with this frequency, how many predictions you do? So would you do a daily prediction on whether a patient needs mechanical ventilation, or could you do that every hour? And how does that fit for the Clairvoyance package?
Yeah, so there are, so currently we define two types of prediction problems, and they're related. One is one shot. So based on an entire time series, predicts a certain endpoint. The other one is rolling sort of online prediction. So every time something comes in, a new data point or a new complete or partial data point, you would then update your prediction for a certain window ahead. So that's definitely doable. Depending on how frequent your observations are to begin with, when something comes in, we would be able to issue a new prediction.
Would you say that window when you're predicting an event to occur, you could also play with that, or it's like in a...
Yeah, for instance, if you want to say within the next 24 hours, well, an endpoint within 24 hours ahead, and something new happens 4 hours later, you can then reissue that prediction. I mean, obviously things get more nuanced when it's survival over a fixed window, but yes, that's doable.
Cool, thank you.
Okay, so I believe we have another Clairvoyance question, and this one's coming from Patricia. So let me ask you to unmute yourself now.
Yes, hello. Thank you for the presentations, very interesting. So my question is about whether it's possible to kind of analyze the latent variables in the time series you are analyzing with the Clairvoyance software. And what I mean here is that, yeah, in the medicine, we also look into some temporal signals coming from the body, so physiological signals. And those, we not always understand what's going on exactly with the signal. So I would like to learn more about the patterns in specific time segments and whether it's possible with this approach. It's clear.
So currently we do not have, it's certainly possible to use latent variable models in the framework. We haven't implemented those yet, but in terms of what, I hope I'm answering this, actually answering your question. So in terms of what segments are contributing more or less to the prediction, right now we do the, so we have InVase, which is instance-wise and time step-wise feature importance. Not sure that's exactly what you wanted.
Yeah, thank you. Well, it's a good start.
Okay, so we have another question on clairvoyance as well. This one's from Peter. Sorry, go ahead and ask your question, Peter.
Hi, thanks. Yeah, so my question is, how does clairvoyance deal with non-monotonic features? So for example, heart rate, which can increase or decrease over time, irrespective of intervention. So how would this affect your modeling of treatment effects?
Yes, so we're not dealing in any special way with the non-monotonic features. So in the models with treatment effects that are currently implemented in clairvoyance, they both use recurrent neural networks to process the history of patient covariates. So they're taking into account this change in the heart rate when modeling the response to treatments. So I don't think this poses a particular problem for what we are doing. The idea with the models for treatment effects is how we handle the bias that arises from time-dependent confounders in observational data. And the way we are processing the features is using standard RNNs.
Okay, thanks.
Right, so I think that's actually all the questions that we have at the moment. I guess if you do have any remaining questions, feel free to just put them in the Slack or something, but I'm not sure we'll be able to get around to them. I would like to ask Mihaela maybe just to share a few quick words. And if during that time anyone posts a question, maybe we can get around to that, but if not, then I guess we can wrap up. So Mihaela, do you want to go ahead?
Yes, thank you very much. Hopefully you can hear me. So I wanted to thank you all for joining us. And it is really our hope that you will engage with us in building a community around not only these different ideas, but also build together software packages that interrelate to each other and link to each other. So many of the questions that you have asked, we believe are very useful and pertinent. So hopefully we can join forces with you all to build more comprehensive software platforms such that we truly enable and catalyze future research in machine learning for healthcare. So please, if you have not time to look at this software, both Clairvoyance as well as AutoPrognosis, please take a look and engage with us. They are by no means complete software packages, they're just beginning, so they can be extended in many ways. So that's the reason we had a little discussion by Zhaozhi on how possibly you can extend them further, and we hope this will happen. Also, I wanted to take this opportunity to say that we really would like to hear from you what type of topics you would find interesting for not for the next one, for the next one we already have a plan, but the one beyond, whether you would like to hear more about interpretability or causality or causal inference, or synthetic data, generating synthetic data for the sake of healthcare applications. So we would like to hear from you what other topics you would like that we discuss and brainstorm about. So, so please reach out and send us messages about that. Thank you so much.
Okay, I think we actually have one kind of general question incoming, and this is from Prona again. So I'm going to ask her to unmute yourself, and this is for you, Mihaela.
Yeah, thanks for, again, organizing this call. I'm really happy to be here. The question I had for you, Dr. Van der Schaar, was that, like one challenge for most of healthcare AI research is like translating these tools into industry and actually being used by clinicians. And as we know, interpretability of these complex machine learning tools is a major challenge to actually help that happen. And I guess my super general question is that how do you persuade doctors to use anything other than shallow logistic regression models or shallow decision trees? Like how do you persuade them to use something more complex than that?
Thank you for this question. So I think we as a community, together with all of you who are interested on this topic, we need to try to carefully build models that are reproducible, that are understandable to the clinicians, that are robust, and hopefully understand in which domains these methods make a true difference and communicate it as clearly as we can. So we are trying to build also a community of clinicians that are receptive to adopting and building new tools. And maybe your question makes me think that maybe a subsequent session should be to invite a few of the clinicians we are interacting with to give their thoughts to this community and this group as to what they would think would be useful to do to kind of get our methods be at least tried out by this community, clinical community, if not necessarily used. So I think it is a long road that we need to travel as a group of researchers and, let's say, computer scientists, engineers, statisticians, applied mathematicians working on these topics to engage with the clinical community and understand truly what they need, as well as explain to them the power of these tools. So thank you for that. I think, so I think we need to engage on all the fronts on trying to really to understand also good problems, because I think we as a community not enough are engaging with the type of questions they want answered. At times we have a set of canonical questions that we like and we think we can address, but often when we bring these methods to them, we discover that there is another way of thinking and other problems that they need to be addressed to really solve problems for them. So, but I will take this as an action item for me to bring maybe a few clinicians to a subsequent session to kind of engage with us and give us food for thought with respect to that. So thank you for that.
Yeah, that would be really amazing. I'm a computational biologist in a precision healthcare startup. So like on all our like interactions with clinicians on like the tools that we develop, like they've always preferred like much simpler models. So yeah, I just wanted to get your thoughts on that, and it was really insightful. Thank you.
Thank you.
Thank you. Okay, so I think we're pretty much right on time to wrap up the Q&A at this point. So all that really remains is basically just to talk you through what to expect for our upcoming sessions and a few other little bits of sort of housekeeping. So our next session will be on December the 3rd. We are going to sort of wrap up this AutoML kind of mini series we've been doing, and in this one, before we start a new kind of theme or topic, we'll just be highlighting a number of different very new and exciting ML for healthcare projects that our lab has been working on. And if you want to kind of keep up to date with the latest about this or about what the lab's doing in general, please do visit our dedicated page for these sessions or our website overall. Also, we do appreciate it if you let your friends and colleagues know about these sessions, because we are trying to kind of build a community and engage with as many people as possible. And thank you all very much, as usual, for joining us, for your contributions, for your questions and your thoughts and ideas. One very final note is that we are still recruiting for PhD students. We do have a handful of fully funded positions that will be starting autumn 2021. We do have a dedicated page for that as well, so please check that out. In the meantime, I guess I hope to see you all next time. Please take care, stay safe, and I guess, yeah, see you soon. Thanks very much for joining us.